Let me allow the screen sharing. So Wendy, whenever you're ready.
Okay. So the lecture in this week is about sensing. So I found an article about the review of cutting-edge sensing technologies for urban underground construction. So it's quite a good review, and it summarized the three kinds of sensing technologies applied in urban underground construction. And first, in many metropolitan cities, underground space have become a network, and some big cities have already used underground space as subway stations, business street, and also some parking lots. So the newly constructed underground structure could cause adverse impact, including soil disturbance, such as metro tunnels under existing pipe or subway stations. And if the underground structure is damaged, adjacent structure and existing surface building could also be affected. The building could crack or even collapse. So to prevent those damage, the advances in sensing technologies offer methods to assess the condition of a structure and monitor its health. And the traditional manual monitoring could overestimate or underestimate the risk and does not reflect the real-time performance. So what to measure and how? The force and deformation are two most fundamental components of construction monitoring. And according to the stress strain curve theory, the relationship between the deformation and the internal force of the object, implying that those two are equal. So the underground construction relies primarily on deformation measurement. And this lecture talked about three types of sensing technologies. The first one is fiber optic sensing. And the advantages of fiber optic sensing is that it's automation, accuracy, and spatial resolution. And the first one about the fiber optic sensing is fiber breadth grading, FBG technology. It could monitor the deformation to measure the strain of key point and observe the behavior of concrete during solidification. And this picture shows a typical urban underground engineering, the subsidence and tilt measurement. And this is the deformation measurement. And this could test the strain and stress in the pit. And this picture shows the principle of the FBG sensor. I prepared a small video about the FBG sensors, but I think it's only 10 minutes, so I'm not going to show it. So another one is the distributed fiber optic sensing, the DFOS, and the central technique of DFOS is the scattering. The scattering technology obtains useful data by demodulating the naturally occurring Raman-Brillouin or relay back scattering signals. And this picture shows the principle of DFOS. And the DFOS is superior to the FBG because it can detect all the section of the fiber, but the FBG can only detect 3 degree, the 0, 45, and 90 degree inside the fiber. And then this paper summarized the different category of this relay and Brillouin and their applications field. So here's the application. The figure A shows the test for a pile. and instrumented with sensor including fiber optics, strain, and the displacement sensor. And this shows the example of the FOS installation at a diaphragm wall in London Clay. And C shows the BOTDR optical fiber to the tunnel lining segment, which was conducted during construction of the Singapore Mass Rapid Transit Circle Line 3. And the second one is the photogrammetry. Currently, the GPS has been applied to monitor the deformation, but it is often inaccurate and has poor signal in underground space. So another application is about laser scanning, but it was expensive and time-consuming. So the researchers focused more on the close-range photogrammetry, and one of its application is the digital image correlation, and the DIC. The DIC calculates target displacement using figure pixel coordinates. And this picture shows the global and camera centered coordinates. And this is the coordinates inside the camera. And here's the captured plane. And they use a formula to transmit this pixel coordinates, and the differences between pixel coordinates of a target point before and after a movement are then calculated. So to further understand the DIC principle, maybe you can search it on Google or the YouTube to get more information. And one important part of the DIC is about the image partitioning must ensure that there is only one target in each subregion. It showed in this figure. There's a tunnel and there's only one point in different subregion to get the photogrammetry. And this picture shows the typical photogrammetry process. First, the calibration, and then the image matching based reconstruction for vertical deflection. And the next step is model-based image fitting for planimetric displacement. And about the photogrammetry, the researchers have had some research about this technique. One of it is the researcher have measured the simulated ground movement by photogrammetry. Here's this research design. Here's a different target with different level. And first they measure this with close range photogrammetry and then compare it with the traditional level instrument. And this figure shows the comparison between these two techniques. And the gray line is the level instrument and others are from the photogrammetry. And the photogrammetry shows the potential of narrowing this elevation difference. Another one is that the researchers developed a photogrammetry system using DIC techniques to monitor the deformation of a structure based on an escalator barrel in an underground station. And this system was successfully applied in the London Underground Railway and other tunnels. And this picture shows the cross-section and camera view. And another application is about the relative deformation of transverse cross-section and vertical deformation along the longitudinal profile of tunnels. And it shows in this figure the different target in the tunnels to measure the deformation. So the third one is improve the conventional sensor technologies. The first one is electromechanical system. They are small, highly integrated, and could sense, process, calculate, and transmission. And this picture shows the double-ended tuning forks. And the principle of it is the mechanical resonance frequency changes along with the actual string. And the resonator was integrated into a closed loop layout, forming a string-related oscillator to measure string. And talk about the limitation of the sensor. The sensor battery limits their service life, but the MEMS sensor has lower electricity consumption because of its micro size, and also the electric it used is lower. And with ongoing energy acquisition research, the MEMS sensor will be capable of obtaining energy from the environment in the future. It could use the vibration in the environment to generate the energy. And also, another type of sensor is the wireless sensors. It reduces the limitation of sensor placement. And this is the process of data acquisition transmission in a wireless sensor network. And these are the wireless transmission protocols used in WSN and 4G, 5G, the LoRa, and also the Bluetooth and Wi-Fi. And here's their advantages and disadvantages. And to combine the advantages together, here comes the 4G Wi-Fi WSN. It combines the Wi-Fi sensor and 4G sensor together to get a long-range coverage and also the lower cost to build base station. So next part is the future trends. Talk about some disadvantages of these three types of technologies. The fiber optics are fragile. So in the future, maybe fiber optics could design some prefabricated machinery specifically for underground engineering. And for the photogrammetry, it always requires a favorable environment for imaging. You need to take picture in the underground space. So you could increase the brightness or using targets with special optical features to improve the photogrammetry. Also, some advanced algorithm could help the photogrammeters to get higher precision. And here is the advantages and disadvantages about the fiber optic sensing, the photogrammetry, and the improved conventional sensor technologies. But the technologies talked here is not widely used in the underground construction due to some cost or some other reasons. But in the future, more developed industrial and commercial system for production would decrease the cost of advanced sensors and contribute to their popularization. So that's all.
All right, thank you, Wendy. So quick question. What is the contribution of a review paper? You know, why people are writing review papers?
To get a better understand of the whole structure.
Okay, so the review paper doesn't contribute to new knowledge, but it's a summary of the existing knowledge, right?
Yes, and also the review could give some new point about the future.
So it's possible, okay, I see that. So it's possible for us to look into the trend of the existing literature and to figure out the future development or trying to identify the challenges and opportunities, right?
Yes.
And also, I don't know if you guys notice that usually the review papers are highly cited papers. You know, if you are entering a research area and you have no knowledge about the area, the good starting point is actually find a review paper, especially the highly cited one. So you will get a sense of the origin of a research area, the trend of it, and also a lot of good review papers actually have this kind of a top-down review of the knowledge area, knowledge domain. So they basically pointed really good research gaps that you can fill. So that is probably the benefits of all the advantages of writing review papers. But nowadays, review papers are very difficult to publish. You have to write proposals to a lot of journals to convince the editor that this review paper will be high quality before you can actually submit the review papers for peer evaluation. Any question from the or comments from the class? No? If not, please use the link I shared in the chat box. And this is a 1D job. All right? So let me share my screen. Let's finish up the big data we left last time. So if you recall, last time we talked about a very unique phenomenon with the increased dimensionality in your data. So when you add more variables, when you add more X, so originally your model performance or the prediction will improve, but after a certain turning point, we start to see this phenomenon called the curse of dimensionality. And because of that, the need for more data points will increase exponentially. So that's why we have two cures to address the modern engineering problems. One is to reduce the dimensions of your model, like to reduce the number of X considered in your model. Another one is, of course, capture more data. But when you capture more data, the process and analysis of that more data, the big data, will become extremely difficult. So we know there's a need for that. And let's talk about quickly the methods we can do. So what we can do with big data? At this point of time, all the methods or tools are actually serving three functions. One is aggregation and statistics, such as you have different data tables and you want to add them together. Statistics is more related to calculating the maximum value, calculating the average value. For example, for Amazon, they might want to know for a certain product, the average click number on Wednesday, for example. So it sounds easy, but when you have big data, it's very difficult. So that's the number one function. And so the terms we use for big data aggregation statistics is data warehouse and the OLAP, the online analytical processing, or what we call queries. And also the second function is indexing, searching, and querying. So for example, let's use Amazon as the second example. I want to know for the age group 20 to 30, like what is the, let's say I know this customer ID and I want to search, last week, what product this person purchased on Amazon. Then you need to use this customer ID as an index and to search to find the value for that, which is the products and all the user information related to that. Once again, this sounds very easy, very straightforward, but it's extremely difficult when we face big data. And the last function is the highest function, is called the knowledge discovery. So for example, if we want to know the most popular products among the age group 20 to 30 on Amazon, or if I want to predict the selling amount of a certain product based on the last 12 months selling volume, then I need a regression model. So this is actually the highest need on big data. So aggregation statistics, indexing, searching, and querying, and knowledge discovery, that's the three main functions of big data. And based on the three main functions and also the related data structure, we do have this ecosystem of big data. This is mapped by Professor Fox from CMU. And so he basically say, based on your purpose, like for iteration and learning, this is more the third function, the highest function when you model something. For querying, this is the first and the second function. I just want to search the keyword. I want to count the numbers. And also for streaming is more like, let's say Twitter, like while people are pushing data into the Twitter platform, I want to do some real-time prediction. Or, I have all the traffic sensors collected from New York City. I want to predict the real-time traffic jams. So it's actually in and out happen at the same time. That's called streaming. So for them, we have different groups of tools and methods. And we have four main types of big data analysis methods or analysis systems. One is called a DAG, directional analytic graphic model, MapReduce model, graph model, and a collective model. So the graph model and DAG model, DAG model, they are very similar. So they're basically based on the theory of graphs. And the MapReduce model is based on the two processes, the map and reduce process. We will talk in a moment. And the collective model is more the combination, the integration of different models. So among the four kinds of big data processing methods, and these are the three functions, okay? MapReduce is the most popular. So MapReduce represents a mathematical or logic method for big data processing, and Hadoop is the name for the entire ecosystem, including the hardware, algorithm, data warehouse, everything. So this is actually driven by Google. MapReduce was first developed at Google, and later become like a golden standard for big data process. So let's talk about this MapReduce system. So MapReduce is a method, like I said, and the name or the brand name for MapReduce is called Hadoop. This is Google, and this is the Hadoop ecosystem. And imagine that you have to process data. Then you need what? You probably need a storage, right? You need an indexing system. You need a method to read the information, to write the information. So this figure actually shows, this graph actually shows the ecosystem of the Hadoop system. Let me swipe this. So we have the Hive for data warehouse. This is actually the database infrastructure, that how we manage the database. This is Hive. The Peak is the data streaming processing. So this is actually a special application for the in and out at the same time, the streaming analysis. The Mohawk is the data mining tool. The data mining is related to statistical modeling. Like if I want to do a regression method, then you can basically use Mohawk. And the MapReduce is actually you can imagine MapReduce is the operation system that is running the entire logic. HDFS is the distributed file system. This is Hadoop distributed file system. So this is how Google or this Hadoop system manage the data, okay? And we also have some secondary service or system. So for example, this Zookeeper is a collaborative service. So if you're talking about online collaboration, like you are company A and you want to work with company B in some big data processing and sharing, and you need to use this service. This HBase is the real-time distributed database. So this is a specialized use of a Hive. I also need to make it faster, make it real-time. So this is HBase. We also have this data logger, the Flume. The data logger is more like the table of content. Like, I have a really big database for my company. And this Flume is kind of like the simplified version that I can see the entire architecture and structure. And also this is a Scoop. This is the ETL tool, extract, transform, and load. This is a table operation, like how I combine different database and how I separate different database. So I know this is look really abstract, but now imagine this, what you are seeing on the screen are different computer programs. So if you are the manager, IT manager of Amazon, and if you want to use this tool for a certain function, then you are going to pick the right tool to realize certain functions. So for example, if your boss now requires you to use the real-time Amazon transaction data to make some kind of prediction, then you have to use this peak to basically get the streaming data. And when you run that kind of mining process, of course, you need to use MapReduce to allocate and to separate the computing load into cloud server parallel computers. And this is how you use MapReduce. And then you probably finally use the Mahat to run some kind of a regression model, statistical model to do that. So now imagine on your screen, you have the 3 programs opening to serve that function. Make sense? So you probably would ask why, why we needed designated software applications for certain function, because this is big data. I just want to give you a quick example. Let me stop sharing this one, but share my entire screen. So this is, for example, I just have this 10,000 random numbers, okay? So I just basically have this 10,000 random numbers, and I just want to sort them based on their value. Let's say from largest to smallest to largest. Now this is actually Excel. We know how to use Excel. It's so straightforward, but just check it out. It still takes, yeah, I know it fast. It probably just took about 1 second, but think about that. See, my computer is still thinking. You see that little loading arrow? Now think about it. My computer is amazing. So I have an i9 CPU and 64 gigabit RAM, and really good CPU, really good graphic card, really good RAM. But still, it takes about 1 second for my computer to sort 10,000 numbers, or do some complex computation, with Excel. Why this takes time? Because this is how we sort numbers. Let's just say sorting numbers from the smallest to the biggest. What happened? What is the algorithm? It's actually, even though it happened really fast, but the logic is quite complex. So let me share the sound of my computer. So let's check what is, this is actually something called a bubble sorting method, how we just sort the number from minimum to, you guys can hear the sound, right? All right, so I think you have a sense. Even though just for sorting that 6 numbers, the computer must do the pairwise comparison like for many times. Now imagine how difficult it is for my computer to sort there's 10,000 numbers. The reason they are filling the happen so fast is because thanks to the modern CPU, they can run, I don't know the exact number, but they can run billions of computation per second. But the picture is different when we are facing big data. Now you understand, the scale of the problem is quite different. So the core is MapReduce and the HDFS. You can imagine HDFS is a specialized hard disk. Like the hard disk in your desktop is managed by the FAT system, or what is the other one? Sorry, I forgot. There are two data file systems today that are popular. One is called FAT system. The other one can manage relatively bigger, smaller, is something called HD. I forgot that. But HDFS is actually a specialized hard disk system for big data. And the MapReduce, you can imagine that is the operation system running on this HDFS hard disk. So what is Hadoop? Together, the two things, MapReduce, HDFS, everything here on the screen, that's called Hadoop. So Hadoop is an open source Apache project, originally started at Google. It's a framework for reliably storing and processing PB data using commodity hardware and storage, which means you do not need to rely on the supercomputers. You can use just regular computers. But because of limitations, so we need a special, because of limitations of the hardware, we have to use the specialized algorithms and methods, okay? So it's a scalable solution. So it varies in terms of computing capacity, storage capacity, and input-output bandwidth. So which means you can use Hadoop to run fairly small project, but you can also use it to easily manage like a relatively big project. Like Amazon is also using this one. The core components, like I said, HDFS is the Hadoop distributed file system. This is the hard disk of that. MapReduce is the method running on that. So Hadoop is written in Java, and it supports Linux, Windows, Solaris, and the Mac operation system, all right? So this is the overall view of this Hadoop. It's a hierarchical and a clustered hardware. So we have something called nodes, okay? The nodes, you can imagine nodes is kind of like a computer, and with some hard disk that can store, let's say, 1 TB data. That's not the exact number, but let's imagine that, okay? It varies a lot. We also have racks. The rack is kind of like a cluster of nodes. Let's imagine in this computer lab, I have 10 computers. So each computer is a node, but this computer lab, I call it a racks, okay? But I also have multiple computer labs, which means I have multiple racks. So that's the first level of that. And then we have a higher level, which is called the name node. And so we can transfer like higher level data with the upper level. So for the same level or the lower level exchange, the speed, the bandwidth is 10 gigabit. It's 1 gigabit, okay? And for the 1 gigabit per second, and for the upper link, which means I'm sending data to some higher level clusters, that's 10 gigabit. So in general, what you need to know is Hadoop is a hierarchical and a clustered hardware. This is parallel computing, okay? And HDFS is the file system, the hard disk, the file system for Hadoop. So this is a PB scale. So what is PB? Just a quick reminder. Let's go back and check it. Here it is. So PB is actually around 10,000 TB. Okay, so this Hadoop runs TB, runs 10,000 TB. Our computer today, or the file system today, can run TB for no problem. So like my computer runs a TB, like this one is a TB level. Let me check the property, NTFS. So the file system that runs this TB level is NTFS or FAT, okay? So the, here it is. So the HDFS, that's actually the Hadoop file system runs on PB. It's managed by a single name node. We will talk about it in a moment. So files can be written, read, renamed, deleted, but append only. What is append only? basically when you make a change to your database, let's say, I change my username or change my password or change my profile information on my Facebook, for example, it actually never delete your previous information. It just append new information to the old information. So it's possible for us to recover the old information. You always leave that choice and you always store somewhere in a server somewhere, okay? So you would question, wow, that means a lot of historical data. Yes, unless you start that kind of a delete action, or if there's a malfunction or some kind of a disaster happen and delete, remove data, the data will always stay there. That's actually the method we are using today. That's called append-only database. It's actually very common for big data. You ask me what is the policy for removing data since the data will keep growing, right? I don't know. So far, there's no written policy, like after 3 years, we delete all data. No, it's still, you have to initiate that. So like if you use Google Doc, it's possible for you to still see some logs from a year ago, okay? It organized for streaming reads of large data. So that's HDFS. And the method, the philosophy of HDFS to manage big data is to break the data into uniform sized smaller data blocks. Now 128 megabit, before it was 64 megabit. And we store the data into something called the data nodes, and we manage them, the location and the keys of them based on something called a name node. We only got one name node for one HDFS system, but we could have multiple data nodes. Make sense? Depending on how much data you have. And so the bandwidth scales linearly with the number of nodes. So the more number of nodes you have, HDFS will allocate more bandwidth for you. So to keep the same level of transfer speed, okay? System is topology aware. What that mean? It was actually a mathematical method proposed by some professor from, I forgot, Harvard or MIT. And so this is actually using the graph theory to optimize the search. So it knows, for example, you guys know that famous bridge problem, like the city, a small town has 7 bridges, and you want to go from, you want to basically go everywhere, and what is shortest path to go over all the 7 bridges, right? That's actually a mathematical problem, how we use the shortest path to cover the most, corners, the most areas. HDFS uses that. So this basically, it applies the graph theory to optimize the search in that big database. Makes sense? That's called a topology aware. And this is actually the graph of that. So when you, let's just use examples to make it easier. Let's say you are the customer of this HDFS and you just uploaded the 1 PB data. Let's say the transaction records of some stock. And so number one is it will cut, the entire data into smaller chunks called a block, about 128 megabit each. And then it will make 3 copies of them, okay? So they basically duplicate your smaller chunks. And then based on some algorithm, like I mentioned, the topology aware, they send your chunks of data into different servers. It could be like some data sent to China, some data sent to Japan, some data sent to US, some data sent to Europe. Even though when you are using the user terminal, you are still opening and reading the one single database, but it could be possible some pieces are stored globally, different areas. And the copies, maybe for one chunk of data, block of data, maybe 1 copy is in Japan, 1 copy is in Europe. That's very possible. But who manages where to find the right data? So for example, I stored the data, I uploaded my data to this HDFS server, and now I want to check, okay, so for Wendy, I want to check her transaction history in last year. So now I need to read the data. So then you are actually accessing the name node. The name node is more kind of like the upper level management system or the table of content. So you say, now search for the name 1D job. And if there's some repetitive name, then search like the driver license number. And then this name node basically stores where the location of this piece of information. So basically tracks that information and send it back, and combine them again, send it back. The actual operations like adding new data, removing data, duplicating data, or merging some data, that actually is not a function of name node. This is the function of the data node. So the chunks of data are saved in the data nodes. You imagine data nodes are servers, okay? The functions of writing, reading, duplicating, moving, removing, deleting are functions written in the data nodes. But once this is done, let's say I just made some replicas of certain blocks, I will report this back to the name node. So I will update my name node, okay? So it's possible that, let's say there was a flooding and you know, the servers in China just got damaged. And will I lose the important data? Ask you guys this question. Will I? No, because I have three, you know, by default, 3 copies and spread them everywhere. So the big data is not only big, but also safe. You know, I make so many copies, so it's so safe. And by the way, guys, I don't know if you guys are aware of that. The biggest iCloud server of Apple is using is actually in Guizhou, China. So basically building in the mountain area in Guizhou, closer to the water. So it basically can cool down, you know, the servers. And the reason they build it in Guizhou, because the servers, the data servers are really, really energy consuming. It requires a lot of electricity and generates a lot of heat. So that's why they basically pick areas, regions where the electricity cost is relatively low. And that's actually Guizhou, China. It becomes a very popular place for data center. All right. So this is the, you know, HDFS. I think now you know, in general, you know, how it works. So you can tell from here, the hardware of big data requires parallel computing, right? So I basically separated one single piece of data into chunks and spread them. But now we do need an operation system that corresponds to that works with that, right? And that's called MapReduce. The map is cutting them into pieces, and reduces, aggregate them again. Make sense? So that's called the Google MapReduce, originally invented in 2004. And in 2005, it became an open source project, Apache Hadoop project. I include the links. So if you're interested, you can go there. And in 2019, it was a milestone for the Hadoop project. So that's Hadoop 3.2, when they separated the resource management and the computing model. So originally, there's this MapReduce model, this Hadoop version. When you do this resource management, like removing some data, deleting some data, adding some data, merging some tables, as well as the computing, like calculating the average number, content, the frequency, that's all one package. But after 2019, it separated them into different functions of package. And the latest version is 3.3.4 Hadoop, all right? So the key features of MapReduce model, the operation method, is designed for clouds. You know that because the Hadoop, the HDFS, the hardware of Hadoop is actually cloud server. So the operation system of that must be working, designed for the cloud server. And also large clusters of commodity machines, which means I don't require special supercomputers. Just regular PC can support this Hadoop system by using MapReduce method. Designed for big data. So this GFS is a Google file system. HDFS, you know that is a Hadoop data distributed file system. MapReduce programming model, you know, we will talk about that in a moment. So here is the logic of MapReduce. Let me just put it here. Let's say, you know, we have a game between UF and A&M, and we want to count how many files are supporting UF and how many files are supporting ANM. What is the most common way to do it? So let's say we have this gatekeeper at the entries, and this guy has a clicker, and he just basically asks every single person entering the stadium, and do you support UF or do you support AM? So basically just a clicker, you know, to document everything, right? Yeah, this is a traditional way of data processing. This is also the traditional way when we try to sort the big data, when we try to calculate the average number with this HDFS system or FAT system, okay? But what are the potential issues, guys? We only got one processor, right? And so this becomes the bottleneck. And the speed really depends on how fast the people move. How fast people move means what? The band-wise, like how fast you can change data. And also the CPU of this person, right? How fast the person can process data. And there's also other issues such as the reliability, the resilience of your system. So if something's wrong with this person or with that CPU, with that computer, then the entire system will fail. Okay, can you guys tell me what could be a smarter solution for that? Like how do we count how many UF fans and ANM fans for this game? Anybody?
Maybe by using the ticket informations.
The ticket information, but still, the ticket information, hold on, ticket doesn't say, right? Ticket doesn't say which team you're supporting, but it's close, yeah.
Getting their, like checking out their UF IDs or something, that sort of a thing, like their IDs.
You know what? That is also not error proven. For example, I'm holding UFID, but I transferred from ANM, so I might be supporting ANM with a UFID, right?
As Rami said, like while giving the tickets, we can, like, there's one form which we have to fill, so we can ask them there itself, are you supporting UF or TNM?
But still, you need a person to count that. You still have one person to count that, right?
I mean, we can make two people, we can make two gates where one side UF can enter and on the other side, the ANM can enter, and you can just click when the person enters, that's it.
That's great. That's actually the spirit of a lot of big data processing, parallel computing. And that's actually what we call MapReduce. First, let's appoint a processor for each seating area. And we call the processor, each seating area processor, this guy, called a mapper. And the process of appointing them to, hey, go to gate 2, go to gate 3, go to gate 4. That process is called a mapping. And we also have, a centralized guy sitting in the middle and continually receiving the aggregated information from each of the mapper, each of the gate processor. So we call this guy reducer. And this process of, hey, how many people supporting ANM from your sitting area? Okay, how many people supporting ANM from your sitting area? So this process is called reducing. Makes sense? So mapping and reducing. Okay, so this is a formal process of MapReduce. So mapping or map means we divide data into segments, which we call tuples, and assign them with key and value. Why do we need a key? It's kind of like when I assign you guys, I assign Suyash, I assign Wendy, I assign Rahib to gate 2, gate 3, gate 4. I do need gate 2, gate 3, gate 4 as the key, so I know which number represents which gate, right? So that's called the key. And the value is what? How many people in gate 2? How many people in gate 3, right? So that's a pairwise system called a key and a value. And remember, how do we segregate them? So let's say now the customer just uploaded 3 files, 100 megabit, 129 megabit, and 250 megabit. So now the mapping will cut them based on the size. Quick question, how many segments will we have from the 3 uploaded files here?
Maybe it depends on the information that we put in the system. So we can do it like 2 segments or 3 segments.
just a quick tip for you guys. Remember, we say MapReduce or HDFS actually builds the fundamental elements of HDFS system is called a block. And what's the size of each block? Remember that? 128 megabit. Remember that, guys? So now, how many segments will you have from the 3 files uploaded by the customer? How many?
Maybe 3.
Why is 3?
Because 100 is less than 128 and 129 is more than 128 and 256 is twice of maybe
Yes,
128.
then how many segments we have? You're close. 5,
So like,
right? 100 megabytes, so I compare that, oh, that's smaller than 1 block. So I basically treat it as 1 tuple. And 129, unfortunately, even though it's very close to 128, but I still have to cut it into 128 and 1 megabit. And 256 will be cut into what? 2 128. And what happened? I threw this 100 megabit tuple to Japan. I threw this 128 to Guizhou, China. And that 1 megabit stays in Texas. The 2 128 megabit from 258, one go to UK, one go to Australia. Make sense? So that's actually happens so fast. And then that's that process. Of course, when I do that, I also assign with them the key and the value. Let's say the key can be the customer ID, you know, like for example, Eric 1, Eric 2, Eric 3, right? So that's the mapping. And reduce means, oh, okay, I forgot one thing. And then depending on the need of the customer, I run that operation separately on the tuples. For example, the 3 files represent transactions from Amazon. And I just want to calculate how many transactions, okay? So 100 megabit, 129. So once I cut them into 5 segments, I calculate their corresponding number of transactions, okay? So the numbers are very small. Let's imagine just a small number. So let's say, based on that, I know this is, oh, sorry. Let me use this example. So let's say I cut a complete data set into 3 chunks. And the request from the customer is to calculate how many times the word cat appeared in my files. So instead of doing that kind of sorting or algorithm on the entire data, now I basically run them on each of the tuples or each of the blocks. So I know in the block 1, it appeared 1 time, so that's 1. In block 2, it appeared 4 times, so that's 4. And in the third tuples, appear 9 times, so that's 9. Okay, that's called mapping. Reducing means returns a list of constructed database by applying a function and algorithm together. So basically, finally, there's a function that aggregate not only the ID. So basically, I check the ID, but also the results, and I apply the same function that applied to each of the tuple, which is the summation, right? And that's basically 1 plus 4 plus 9. So I know this is 14. Make sense? So instead of running this kind of aggregation or summation calculation on the entire database, I cut them into 3 pieces. I calculate the frequency in each of the chunks, each of the blocks, and then I aggregate the result once again. So that's 14. So this is, imagine this can also be gate 1, gate 2, gate 3, fans of A&M 149. And then the total would be just 14, okay, MapReduce. So this is actually an example I found online, like how they split the entire data. This is input file. Imagine this is customer uploaded the file. The mapping one, basically each worker here is actually a computer, okay, which is given a name worker. So I just basically split the data the file into chunks of no more than 128 megabit and send them to the workers. And then I basically shuffle them. And there's also shuffle process. The shuffle process is to ensure the safety of the data, right? So if I don't use the random shuffle, I could be just sending all the blocks for a certain time period to Japan. And if something happens there, I lost all the data, right? So the shuffle is basically I just shuffle them or send them random locations. And then user program basically means what the user requires, like I want to calculate the average number, okay? So it sends to the master computer, and basically the master computer will give orders to each of the worker to do the separate parallel computing. And finally, we have this reduced process to aggregate the result. And finally, we generate this output. So this is the MapReduce. Let me give you this example. Let's say the original file I have is just a text file. And in the text file, I have some words: deer, beer, car, and river. And my request is to calculate how many times the words appear, like how many beers, how many rivers in this text file. So number one, I split them, okay? So I just randomly split them. So for each of the block, I have, some information. And then I basically map them into some kind of a worker computer. So I start to run this counting algorithm. So I know for this block one, I have 1 deer, 1 beer, 1 river. For the block two, I have 1 car and another car and a river, okay? And then during that process, I do the shuffling. The shuffling can be random shuffle or can be driven by the request. So for example, in this request, I want to do the aggregation. So this is more kind of combining. So the request from the server, from the master server, is combining the same word together. So then this one basically say, hey, all the beer come to this box, all the car come to this box, all deer come to this box, all river come to this box. So after that, it's easier for the reducing process to calculate the frequency for each of the keys. So the beer, the car, the deer, the river, that's actually keys, and followed by the value of them. So I basically calculate the frequency for each of the shuffled data tubes. And finally, the result is reduced result is I combine them together as a single output. So this is MapReduce process. And once again, you would say, Eric, this is so easy. Just by looking at this one, I definitely know I have 3 cars, I have 2 bears and 2 deers and 2 rivers. Why should I do this? How about this? Can you just give me the quick answer just by looking at it? No, of course, no, right? And of course, if just imagine, there are more, I don't know what is the number that Amazon is processing, but imagine it could be billions of lines of data. And they need the answer so quickly. So parallel computing or mapping and reducing and corresponding hard disk system, HDFS, is actually the only solution to ensure that. Okay, so this is the logic. This is the principles of MapReduce, HDFS, and Hadoop ecosystem. But to a big data processor, like somebody heard about Amazon, what is the daily work look like? What is the computing process look like? This is how it looks like.
Let's take a look at how MapReduce actually works by running a MapReduce program and looking at the output. So as you remember from previous lessons, MapReduce essentially, you create 2 programs. One is a mapper, the other is a reducer, and you give those programs to Hadoop, which then will distribute them among all the nodes and run the mappers against all the files.
So guys, let's finish this video. It's an 8-minute video, and after this, let's take a 20-minute break, okay?
Files that feed into your process, and the reducer will take the output of each of those maps and put it back into
what's that?
Some output that you can actually use. So what we're going to do is run a MapReduce program that will summarize the word count in a bunch of books. And those books we looked at in a previous lesson are these. So we have Beowulf and Great Expectations and Fairy Tales and so on. So the input files that we have are a bunch of unstructured data. You don't get more unstructured than this. A lot of words in here. And we're going to do something very simple just to summarize how many times the word squashing occurs between all of the books. So we're going to combine them all together and analyze them. So fairly straightforward. Let's see how we do that. So here is a list of commands that will do the entire process. We'll just take them one by one. So here we're going to use DFS to put the data into HDFS. That's actually what this second command does, and we did that in the previous lesson. And the next command is going to remove our output file. So we're going to summarize all of these text files, and we're going to dump that into a folder called Words by Book. So this command just cleans out that folder so that there's nothing in it when we start. Here's the program that really kicks off MapReduce. So this is some, we have some cleanup to do beforehand. Then the MapReduce is going to really analyze the files. And our mapper program is this book text mapper, and our reducer is book text reducer. Let's take a quick look at those and see what those look like. So here's book text mapper. All this is going to do is it does ask the environment, what file am I working on? Because it needs to know that. And then for every line in the file it's been given to work on, it's going to just strip out spaces at the end, split the line into a list of words, and then for every word in that list it's going to print a line. Here's the file name that I'm working on, here's the word that I just saw, and then it's just hard-coded as 1. The mapper doesn't try to summarize how many times the word occurs, it just creates the detail leaf data that then the reducer will summarize. So that's the mapper. And we can test that mapper to see how it works. Let me just open a command prompt here. And I'm going to go into my Hadoop. I have some code samples. If I go into MapReduce, I actually have a script called testmapper.sh, and that's going to take one of this book I have in my local folder, put it into the screen, and then run the mapper test on it, which is basically the same script we looked at, and then see what it does. And this will help just so you understand what the mapper is producing. So the mapper is producing one line that has the file name, the word it saw, and 1. But these are detailed files, so you'll have to kind of look that they won't summarize the data. So in here, the word the was detected, and that number 1 was kicked out. But before that, the was detected against up here too. So the could appear many, many times within this file, and every time being counted as 1. It's the reducer's job to add up all the 1s. So let's look at that reducer program. So if I open the reducer and take a peek at it, the reducer is a little more complicated because it has more work to do. What the reducer is going to do is take the output from the mapper programs, split that by that pipe character that we used to delimit within the file name and word, and so it'll get 3 arguments. One will be the file name, then the word, then the number. And there's just a loop in here, so it will loop through, and as it's given its data, which will be sorted, it will detect whenever the word and file changes and kick out a summary line for that. So here's the current count. So at the end of the reducing process, all those the with 1 will turn into the with how many times that occurred. And then that will get aggregated among all the books that got summarized by all the nodes, and then were combined. So that's what that is going to do. Essentially, it's going to transfer the code. This is going to move the code to the data, and Hadoop's going to do that. And then when that's all done, the output is going to go into this folder called User Hive Warehouse Words by Book. We're putting it in Hive because in a subsequent demo from this one, we're actually going to turn that into a Hive table. But in this case, it doesn't matter. It just is a file that we're going to put into an output folder. And then down here, I'm actually just a little bit of demo, just copying back that Words by Book file so we can look at the output of the reducer. So let's go ahead and run that. And it's going to do all these steps, and they'll kind of fly by, but so pay attention. Oops, not test. So it's going to be run full shell. So that's going to delete the files. As you can see, it deleted them. And then it will actually copy them all back into the folder again. And now the MapReduce job is running. And what you can see going on here is it says running job. And to the console, it will actually start telling you how much of the mapping is done, how much of the reducing is done. So this is a batch that's running. Another way to monitor that batch is from a web view. So if I come into this folder and refresh this, I can see in my running jobs I have this streaming job running. That's the one I just submitted. If I click on that, I can actually see the progress of that job. So it has 28 total maps. 2 of them have completed. Reduces just 1. one reduced job. None of that's been done yet. And as the job runs, I can actually see this will change and it will progress. So I don't have to be on the console to see the progress of this job. I can do it from this web view. From the console it looks like that. So remember, every file is being passed through a mapper, and then the reducer, as soon as 2 files are available, the reducer can start reducing. And then as more come through, it can continue. Again, web view, terminal view. So I'll stay in the terminal. So we can see this finishes up, and the map will get to 100% before the reduce. But then once the reduce is 100%, then the job is done, and we can look at the output. Okay, so to the console, we've been logged a lot of information. So the reduce finished tells us it completed successfully, and then we get various statistics like how many bytes were read, how many were written, and so on. And the meat of it is, this is the output of that. So user, Hive, warehouse, words by book. If I go back to the system, I can look at where that was written, warehouse, words by book. And since the output is relatively small, it's only 24 megabytes, it didn't exceed the block size. So we really just got the one part, one file, and that's fine. If this is a very large job, we might have multiple files here that together make up the entire table, if you will, of words by book, but this one just has one. And if we look at that, now we can see that Arthur, with an exclamation point, occurred 10 times over the course of all of those books. And then as I scroll through, I can see how many times various other words appeared. I can also see opportunities to improve my script. My script isn't getting rid of these punctuation marks, so I'm actually getting nothing question mark and nothing period as being different. And subsequently we'll fix that later, but now you can get the idea. So later on, we'll actually take this and push this back into SQL Server. We'll make Hive tables with it and do some various different things. But that's effectively a basic intro to using MapReduce and creating MapReduce programs.
All right, guys. So that's the HDFS. Let's return at around 5:33ish. All right. See you guys then.